Is everybody ready? So what I'm going to ask, a bit of feedback. Guys at the back, if you can't hear one of the presenters clearly or it's a bit low, could you just please raise your hand to indicate for the presenter to speak up? Okay? And guys, like I said, I'll be giving a 10-minute warning before the end of each presentation. So, next up, we've got Chuck Hansen. He's the founder and chairman of ElectroScan. And before that, Chuck owned and ran Hanson Technology. We've got over 30 years experience in the water industry, and he's going to be talking about ElectroScan and concepts and benefits. Welcome, Charles.
Okay, thanks so much.
Chuck, sorry.
There we go. How's everybody doing? I win the contest. It's Donald Trump. He says he wins, but I win because I came the furthest. So I came in from California yesterday, stayed a half a mile, and of course I got the inbound wrong. So it took me at least 22 minutes to get here. So look, I'm gonna talk a little bit about ElectroScan, but we're kind of at a point now where condition assessment, it always used to be how do we prioritize things to fix. But in the US, we're having some recurring issues with assets that have just been put in place. And so the quality assurance of newer assets to make sure that once we put them in the ground, they're gonna last as long as we want them to, is now become a fairly large issue. We've had some very interesting news just for our company for a while. I'm just getting back from Tokyo, Japan. We've now been awarded, after a year of intensive study, certificate number 12, which is on water tightness, the use of this low voltage technology to assess sewers and their water tightness. So that was in August. WRC, we've just kicked off this month a project, one of which my good friend Julian Britton is going to talk about with Wessex, kind of really introduced us to the UK British market back in 2013. So we just kicked off that project and also some work with Thames Water. So WRC, which is our exclusive representative here, so that was a fairly significant thing. And just so we're current, as of yesterday, we finished several intensive day with IKT. Both Peter Henley and another associate of mine were in Germany doing some very interesting benchmark tests. And the other thing that has been going on is in the United States, this technology now has been codified in the EPA's main book for sewer operation and maintenance. And it's now recommended for all pre and post assessments over CCTV. And this is a picture of Ken Carey, passed away a couple of years ago. So today's topic are going to be pretty straightforward. First thing is we're just going to talk about the uses. How do you use this technology? Some of the examples for that. So how are they applied? Some people call this focused electrode location. I had heard about it over 10 years ago, but this came off as a German R&D project back in the 90s. And I actually was at a UKSTT Awards banquet 2015. I don't know if it was not too far from here in Birmingham. And we had an award working with Severn Trent. I know some of the folks from Severn Trent was here. And WRC had just won an innovation award for the same technology using kind of an older brand of this that they were looking to add on to Sahara. So virtually the only two people on the planet that use this low voltage current was WRC and ourselves, and so yeah, it was kind of a match. So we'll talk about some of the uses. We're going to talk about some of the scientific. I'll try and put it in terms that I can understand it. Looking at repeatability, how often does this thing, can you get the same results? Field operations, and the last thing is, which apparently is a very common saying after yesterday with Theresa May at the United Nations, value for money. So apparently we need that, and how we produce sewer pipes as in services for the United Nations. So we'll talk about those things. Uses. There's a lot of uses for this technology, But when we get down to it, we kind of look at putting them into two categories: pre-rehabilitation, condition assessment, and post. And we will look at post-rehabilitation. That there is this initial certification. Did the contractor deliver me a leak-free pipe? And with a lot of these pipes, we need to kind of look through it over 1 or 2 rain cycles. And so some of the warranties, if they're a 1, 2, 3, 4-year warranty, we may want to go ahead and re-look at that pipe right before its warranty expires, because we want to make sure we're getting that value for money. About a year ago, I really kind of started my career doing the TV inspection project for Houston, Texas in the 1990s. So I'm 61. I've had a lot of, I'm a cosmetic surgery science, so I appear, younger than I really look. It's like that mirror, objects will look closer. So it was interesting when we were looking at pipes a year ago, and then I get a phone call after this happened. And so 2 weeks ago, I was called back in because of this situation. We use water. We like pipes full. You can't get a pipe fuller when you get a situation like this. So we were asked to come down and look at some of the situations when the pipes were running fairly full here. What they were worried about is the timing. And let's be very clear. When I have a catastrophic flood event, if I have a customer that flushes their toilet, that is going to go directly outside. I mean, it typically, there's nothing that you can do about that. But what we tend to see are situations where we get a lot of rain. That rain is going to percolate down into the pipe. It's going to come into the joint, into leaks and defects. But if I had sustained wet weather, and that pipe is now full, and it's backing up into homes, I may very well have situations where I will exfiltrate out of the same location that I've just infiltrated, creating some very high bacterial levels around that. So one of the things we were asked to do is take a look at some downtown pipes. You saw the downtown that was flooded. This was actually an area that had flooded before. And so they said, well, look, we've got some issues with our moderately large diameter. They were 20, 30-inch U.S. pipes. And so we started taking a look at a section. I'll share some things that we looked at here. These are results from scans. What we do, what this ElectroScan technology does, is find holes. And we tend to go through some calculus to come up with each defect having its own standalone estimated liters per second. The interesting thing about this is that we were looking at not just concrete pipe, which of course in large diameters, a lot of hydrogen sulfide deterioration on those, but also a fairly old 10+ year cured in place pipe. And when we looked at that CIPP, we noticed a lot of pinholes down at the bottom for a 10-year-old pipe. One of the things that this technology is able to do, differentiate itself from many others, is when I take a look at a pipe, and it's perfect, I want to try and measure anywhere that electrical current can go through the wall, in this case, liner, through a host pipe and return it back to a grounding source, kind of an internal circuit. It's kind of a interesting kind. I'll go through in the next part. When it's not watertight, electrical current will pass through that liner and return, and I'll measure that, and I'll determine the size of the hole that's in the pipe. And 9 times out of 10 will not be seen with CCTV. In fact, Julian and I were together when I videotaped this. Remember, Julian, we were in Bristol, and Roland came, and he brought one of his samples from IKT. Unfortunately, They're not meant this way in the R&D back of the factory. But depending how cured in place is installed, it can be quite permeable. This is a 12-month-old sewer main by a national US contractor. So one of the things that we've been looking at is just, well, you know, if it's just once every once in a while, no problem. Unfortunately, we are actually finding 1 in 5 CIPP can have an estimated leakage or defect flow rating over 109,000 liters a day. So it's a non-trivial thing. So that's post-assessment, if you will. So we heard the example of Hetch Hetchy. You know, I don't know if you've ever heard of the Yosemite Valley, but Hetch Hetchy almost looked like, back in the day, it looked like Yosemite. And so what they decided to do is kind of shore it up a little bit, and so that became the Hetch Hetchy Reservoir, and that's where San Francisco gets their water. Interestingly, San Francisco is a combined sewer system, so it's sewer and storm. It's only about a 1,000-mile system. But what they've got their problem is at high tide, water was coming into the pipe, and at low tide it was going out, which I thought was a fantastic pre-treatment capability. But apparently microbiologists did not agree with that. Since the beginning of the year, all wastewater rehabilitation must pass a FEL test to be certified. This is any new pipe, any rehabilitated pipe. So that means that before that contractor is approved, and since the first of the year, they published 55 million pounds of bids using the standard. A week ago, we were asked to come and take a look at a few pipes that were just put in. New clay pipes. What could be possibly wrong, right? Let's take a look at one of them. Leaks at every joint. We had actually, the crew rolled up on the site because they wanted to surcharge that pipe with water. They connected that to a hydrant. I said, so what have you done? I said, well, we've been putting water in this pipe for an hour and it doesn't seem to hold. Well, this is why. Leaks at every joint. So looking at standards, looking for ways to kind of come up with these. Doesn't seem like it's thinking. Hold on. There we go. So it used to be that they relied on CCTV to look at things, but when we started looking at comparing defects from CCTV versus defects from a leak standpoint, CCTV was missing 90% plus of where openings were in the pipe. So that was one of the reasons that they changed the standard. They use a new ASTM and also that US. So what are the concepts? How does this thing work? You know, how do you actually find stuff this way? And let me tell you how I got into business. In 2010, I get a phone call from this guy, ruined my entire life. And he was saying, look, my old students, Ken probably, I think, was in his 80s at the time. My old students were finding defects in CIPP they weren't seeing on TV cameras. And literally, he said, Chuck, do you know of something that would help that out? Prior to that, I had a small software company. I started with my brother and my father in 1983. I was lucky enough, I sold the company in 2007. And that was it. I was completely out. I was done. No more public works. I'm out. It was just a party all the time, which was great. So when Ken called me, I was getting up maybe 2 or 3 o'clock in the afternoon at that time. I said, so Ken, what do you want? You want me to do a polygraph test for CIPP? I said, stick a camera down. You can see all that with cameras. you need kind of one of these things. Okay. Did you? Was the liner leak free? So I had, you know, as a software company, we had about 1,000 clients. We had 70 people in the Melbourne office when I sold the company. But I had heard of this German technology, this focused electrode leak location. IKT had looked at it in 2001. I said, Ken, let me get my hands on one of these things, and we'll shoot a couple of liners. So we did, and again, things started coming out. We started finding defects that TV just wasn't even close to. He says, Chuck, let's do this. Let's go look at a clay pipe. Now, you know, I don't know if some of you are my age or around there. You know, we've got, Harrison Ford's got his new Blade Runner movie out. That's the only camera that I know of that could look up to the joint, and turn left, and then move just to see if we have any space still left there. So, you know, and apparently cameras can't really do that now today. So, as we started looking at them and seeing defects and actually digging up trenches and doing open trench leak testing on these things and jumping down and seeing, oh, they didn't tighten the fern codes or they didn't tighten this joint. We really had something there. So this technology isn't any of these things. So we're not laser, not sonar, we're not looking at debris in the field. It's not a video micrometer, to measure the size of the crack, or a packer to test out some things. It's not any of these. It's not infrared, not ultrasonic, not LiDAR. The science is a little bit more basic than that, and it's as simple as this. We know electricity likes to be on a current, and we know it likes to close the loop. So what if we set up a metal stake on the ground, and on the same circuit, we wrap that around, we put it in a probe, we stick that in a pipe. And we stick that into a non-conductive pipe, so not cast iron for now. But let's say it's a plastic, it's CIPP. It's something that we shouldn't allow, that should not allow any electric current to go through. And if we can actually assess 360 degrees of the wall of the pipe as we move through, to focus that very intently, well, if there's a slightest pinhole, that electrical current is going to want to return and close the loop. If the wall of the pipe is perfect, it should be dead flat. What you need is water. Somehow, you need to trick that middle inch, 2 centimeters, around that probe, because water is the conductor. Water allows that electrical current to move from a probe to the wall of the pipe. So there's certain ways that we do this, and also WRC does that with funnel cones. Kind of, if you have a dog, you have an Elizabethan dog collar, so that's where we kind of do that. And so here's what electricity looks like. This is to scale too. All electricity looks like this. You're an electrical engineer, I'm sure you attest to that. This is what it would look like in a pipe. We use something called a tri-electrode array, whereas we want to pinpoint that, so we'll use 2 sacrificial currents, and what that does is that just sharpens us up, so we're going to be real tight as we go through that pipe. So I only want to allow that very thin, and I want 1 centimeter accuracy, that very thin piece that goes through. So if I can do all those things and temporarily surcharge around only the probe, and if I somehow knew how to measure the amount of current, the area under the curve, essentially, I've just figured out the hole in the pipe. The area under the curve is kind of an interesting thing. I I could barely talk to I have 3 daughters and a son. My 3 daughters are still in high school. And they all know the area of a triangle. It's base times height divided by 2. Yes, there it is. So as I look to additionally calculate areas and integrals, and maybe even use what's called Riemann sum to focus on that, I want to figure out the quantity of the current that's moving through that hole. That allows me to do that. Now, there's 3 things I need to do in the science of holes. I need to, first of all, know the size of the hole, size of the orifice. Sorry about that. Okay. I need to know what the groundwater condition is. Soil resistivity, which is tough for me to say too, is always important. But I need to know the groundwater. In our models, unless you pay us more, we assume generally a 30 centimeter head over that. I also need to know the gradient of the pipe, and we assume a 1% gradient. We put those things together, we can scan that pipe. And because I've been doing software for a while, instantaneous data is communicated up through an Amazon cloud, which is processed right away, and I have a full report in under 10 minutes anywhere in the world of where the defects are and what each defect's estimated leak is quantified as. So these are the reports that are just generated. My phone's kind of blowing up because at Rackwell we have a project, a 16-kilometer project in the Middle East right now. It's so hot. I went over there. It was the low at night was 102, and I literally came back losing weight just from sweat. And you sweat too much where you're drinking so much, but you never having to go to the loo. So the data that we get, this is actually from one of theirs from 9/17, so just a couple of days ago. So and these are all pre-commissioned pipes. There's no sewers on these pipes. And they're filled up at high tide, so they want to know how bad is it. So getting that information kind of is. So the other thing in reading these things, just to make it very simple, is we take a look at the height. We want to take a look. Size matters. So we want to take a look at the area under that curve to really look at it. So just because this top one had the fastest return, doesn't mean that's the biggest leak. We want to look at the area. We want to be able, within 10 minutes of finishing this thing, we want to be able to have the data of the start, the end, the height, so we can calculate which one is which. Who's here from Thames Water? This was really irritating me. Yep, you, okay. So Thames came to WSC, opened up one of the servers. I don't know if you did. And so I just wake you up a little bit. Thames was very, well, how repeatable is this? Does it get the same answer every time? Because we always know if we have 2 of the same TV guys trained by the same person, looking the same, they'll always come up with the same defect call out. So the day that we were at Thames came by, I think we did this pipe 8 times one way. I said, okay, do it backwards. So we had to flip the bottom one around. So repeatability is what I loved about this. But then what I also liked is we had a client that's looking at a 700-mile, 1,000-kilometer project. So we've got to have 10 to 20 rigs out there, depending how long they want to take. So they said, look, we want to see you do this with different equipment, a different crew, different software, in different seasons, 4 months apart, with slightly different totals, but all the defects were identical. That's one of the things we measured the last 2 days with IKT. We actually did 2 days. The first day was nearby, taking a look at some live pipes that they had actually done sectional CIPP. And then yesterday was spent all day in the quote-unquote lab, kind of looking at things. So we did about 60 scans yesterday. People all the time ask, well, what about electrical interference? And so one of the things we wanted to do is I think the most congested area is probably the Ginza. So we were scanning there just to see if it really made a difference and interrupt those, and it doesn't. This is a high frequency, low voltage current that we've tested up to 3,000 feet to return. So it's kind of an interesting trick for that. And that's why we're really pleased with the Japanese sewer agency spending the last year certifying this in their tests to actually have something that was with water tightness. I was happy to go over and talk about that. A couple of different ways we do, whether it's a truck-mounted unit, whether it's manual, and the thing that we look at is holding back the water. I mean, when you start getting over 400, 500 mil pipes, it's tough to hold those things back. And when we look at large diameter, if we do a large diameter, in some cases we may plug an end, so we have water as full as we can for that section, but we will only detect openings from a water line and below, because you need that current to go look at that. So what happens when we have a lateral? Well, we generally like to have a kind of a 6 foot surcharge pipe as we go. So as we go down, we like to have a little excess water, so it may go up a lateral, maybe 1 or half a meter. So that way we can get the entire connection to see if that's good. But generally, it's not like it hits the lateral and goes out anyplace. It will only be from that water level below. So you have a top hat that only goes up half a meter. We may find out what that is. Now, the problem is we won't tell you what clock position. We haven't done that. We've got tests on it right now to tell you the clock position. Good thing we don't rehab on a clock position basis. But we are accurate within about 1 centimeter. So reviewing it, some of you know tools like InfoMaster, Innovise. I forget who owns them this week, but and then now having those being prioritized in some of the models. We've loved the relationship with WRC ever since I think 2015. Been working with them, so you might have seen us on that. They've just done a new website. They've got an interesting case study that's out there. But where we really see the advantage and where a lot of the tenders are moving in the States is they're desperate to quantify the reduction in flow. And they want to have kind of a basic baseline. How much did a pipe leak? And then how much did it leak managing to zero? How much did it leak after rehab? And that difference is going to be the reduction. And so, in a lot of cases where we do a pre-CCTV to inspect a pipe, we start on the left. That was the pre that was done. Here's the post. I mentioned you saw the pinholes. That was 3 years later that finally televised that. But in taking a look and then seeing some of the ElectroScan readings over there, how do you manage that? How can you quantify that? So it's not just, gee, we TV'd it, looked okay. So what we're now seeing tenders like San Francisco, where we have a liters per second of what that pipe is leaking at directly after the curing is done. I mean, literally, if a liner company tells us, hey, we're done, we'll do it again. Look at this case. I boxed these two, and I had a total. Look at this. They got rid of all of the smaller leaks. What happened here? These lines actually look bigger. I said size mattered. That's not the size we were going for. Take a look at the videotape. And they had overcut the lateral so much where there was no hole before, which is a massive hole. You can just see dirt. So you want to make sure that when a contractor has their work to line a pipe, what we want to do is we want to make sure that we don't have a 7% leakage. We want to get those repairs so we are managing to zero. There's no ASTM that says a pipe must never leak. In the States, I think they have, I think it's either 100 or 150 gallons per day per inch diameter mile, and that equates to other things. But in taking a look at this, what we want to do is we want to make sure that we are reducing as many of those leaks as possible. The other thing, this may not be a problem over here, but a major problem that we're now coming up with is not only are we finding liners permeable, where water can pass through them, but it's having some other issues as well. It was back in 2009, I think it was the first study by the Virginia Department of Transportation that even brought up that, hey, the liners that we're talking about, not only do we have styrene that's been coming through the system and contaminating some of the water, but because the liner is permeable, it's also passing through that as well. The other thing that's come up in the last 18 months, we've had 3 studies that are all discussing steam-cured liners. And not only coming up through that, but measuring a high level of VOCs. And where most people say, oh, that's just steam, that's harmless. We are not finding that case out. So you see something like this was the city of Los Angeles. This was 1,000 times higher than the EPA's standard. So when we see things like this in newspapers, where they comically call this as the workers taking a steam bath, this is not good. So I did bring, state of California just had a major event, happened in 2016. They just published a statewide CIPP alert. Anytime that steam curing is done, watch it. They had measured, it not only sickened the whole family in his home, they had measured high levels of styrene for a 3-month period. And I've got copies of that up here when I'm done. So just in conclusion, I'm going to talk a little value for money. Yes, just to be current here, right? So we already talked about this before. I think John had a great example of that for hedging, of only doing where you have problems. And what we are finding from a CapEx avoidance issue is here in the UK, for every meter that we can find that's good, that has no leak, just because it's old, I mean, just like me, just because I'm old doesn't mean I'm still not good. Same thing goes with pipes. Some of these pipes are absolutely still outperforming some of the newer ones that are coming in. And so if we can take those off the list, we're going to be saving 250 plus pounds per meter. The other thing that we see, value for money, make sure you're getting the highest quality pipe. I know they have a term for some CIP around here called flour and water. I don't know why they would call it that. But, you know, it's a known thing in a contract. I've been around contractors, you know, a lot of years, talked to a lot of them here. But, you know, taking a look at making sure that any lining, no matter what the inversion process or capability you have in there, make sure that's a quality. And make sure that it's evenly lined. And there's a whole laundry list of things to do. Used to be, people never thought, oh, it's a wrinkle. No problem. Unfortunately, that wrinkle is cured at that point, at that pipe, more than likely incorrectly. Now, UV will have a different thing. If I had a page book up here, you know, UV wrinkles, it could just be the first one, so that may be less of an issue with a UV line pipe. But I've got a felt liner. 9 out of 10 of the leaks that we find, the wrinkles, have a defined pattern and water passing through them. It's not just, oh, it's okay. And I see some of the specs. Oh, if it impedes the flow, let's go in there and grind it down. Yeah, that's the worst thing you can do. Overcooking. Yeah, it looks like the surface of the moon. I wonder if water gets through that. Yeah, it does. It looks pretty spacey. And we haven't seen a top hat that we've liked so far. So, you know, Napoleon once said, war is 90% information. This is big data. I've never really, you know, with a 100-meter pipe, there may be up to 20,000 data points. And some of these charts and graphs look really nice. No, they're actually little points of data that we have. And then I'm a big science fiction fan, so you know I always like this saying: any sufficiently advanced technology is indistinguishable from magic. That's kind of what I saw when I looked at this and some of the improvements that we did in here. So with that, I'm turning it over to my mentor here, Julian.